Hey, everybody. Thanks for joining us today. My name is Eli. I'm on the blockchain security team at Coinbase, and I'm here with Arash from our applied cryptography team. Today's session is about MPC, the MPC library that Coinbase recently open sourced. As always, please observe the disclaimer at the bottom of the screen. And Arash, if you're ready, please take it away.
Awesome. Thanks, Eli, for the introduction. Let me share my screen and start. All right. Right. So, yes, thanks, Eli. I'm Arash. I am part of the applied cryptography team in Coinbase, and I'm presenting MPC, which is our open source MPC key management library. And this presentation is essentially a continuation of what Eli presented a couple of sessions ago about best practices of key management. I'm going to go into more details into MPC by first introducing what MPC is, how can it be used for key management. Then I will demo how our CBMPC library can be used to key management, so generate a key, perform a threshold signatures, and so on and so forth. And then I will end by going over CBMPC's features and the properties and what it offers in general. And of course, I'll end with leave some room to answer any questions that you might have. All right. So let's just start with MPC. Secure multi-party computation, or MPC, is a subfield of cryptography. It is very well researched. It started in 1980s, and thousands of papers have been published in this field. It was purely theoretical up until a decade ago, but in the past decade, it has become extremely practical to the point that we have deployed it in larger scale inside Coinbase to secure customers' funds. The idea of MPC, in a very short sense, is to perform computation on private data. So you're probably familiar that we can protect private data at rest by encrypting it and putting it in a database, right? We can protect the data in transit by using HTTPS or again, some sort of encryption and sending it over the wire. But how do we protect the data when we are doing computation on it? So that's the part that MPC is focusing on. And the M in the MPC, it stands for multiple parties. And throughout this presentation, I will use parties or machines interchangeably. In the MPC world, we have multiple parties. Each of them have a private input, and they jointly want to perform a computation or a function on their data. Okay? And they care about two important properties. The first one is privacy, meaning that none of these participants want anything about their private inputs to be leaked other than whatever is the output of the computation. And they, of course, want to get the correct output. So, for example, let's assume that the parties have some number and they want to compute the average of those numbers. So they don't want to leak their own number. So that's the privacy part. But at the end, they want to get the proper average. So that's the correctness part. The important thing about this MPC is that the protocol still maintains these properties even when we have malicious adversaries. You can think of malicious adversaries as attackers or adversaries who are compromising a machine and are on the machine and actively doing something bad. So it's not just stealing some data and going away. They are on the machine. They are changing the code of the machine. They are running a different program. They're doing whatever they want. So that in that sense, they are malicious. They are not just static or semi-honest and sitting there. So they are actively doing something bad. And in the MPC world, we prove mathematically that our protocols are secure even when we have such malicious adversaries. All right. So that was a little bit of abstract high-level definition. Let's make it a bit more concrete by talking about a toy example. Well, let's say we have a couple of cryptographers. They each have some salary, and they want to find the average of their salaries so that they can understand whether they are being underpaid or not. Okay. Of course, each of their salaries is private. They don't want to leak or anything about their salaries, right? So that's why we want to have this protocol. They don't trust each other, of course. Their salary is their private information, and they don't trust anyone else. So they need to do some sort of computation, run a protocol among themselves to be able to achieve this. So let's see how we can do this with a simple toy example. Alice is earning 120K, right? She is going to choose a large random number, something very, very over than what the typical salary in her field is going to be. So for example, 652,195, right? And then she's going to add that to her salary and send the result to Bob. So notice that when Bob receives this value, 172,195, I'm going to drop the 195 for the sake of the simplicity. 772K. Bob cannot tell what is Alice's salary, right? Because Alice's salary could have been 100K and the random number was 672K, right? Or Alice's salary could have been just $1 and the random number was 771. So just by looking at this number, Bob learns nothing about Alice's salary, okay? So Bob is going to do the same. He's going to add now his salary to this number and send the result to Eve. So the result is going to be 877K. By the same logic, Eve doesn't learn anything about Bob's salary nor Alice's salary. Eve, which is being underpaid, is going to add her salary to the sum and send 942K to Alice. And Alice, at this point, can subtract the original large random value, get the total sum, divide by 3, get the average, and then announce the average to everyone. So this was a very simple protocol to show that we can achieve MPC, we can achieve computation over secret data without revealing anything about our private data. Okay, so this was just about salaries and averages and whatnot. You might be wondering, how does this relate to key management? So in the context of key management, we have a private signing key, which is shown as SK, short for signing key. And our parties are going to have portions or shares of this signing key. So each party is going to have a private share of the signing key. And the function that we want to perform, or the computation that we want to perform, is going to be the ECDSA signature. So we want to sign on a message using ECDSA, given that the private key is that SK. So the privacy property is that we don't want the full signing key to be revealed to anyone. Okay? And the correctness property means that if everyone agrees on the message that they want to sign, at the end, they should get the signature on that message. So if we have these two properties and a protocol that can achieve that, we get a very important security advantage. And that is that we have removed the single point of failure, because without MPC, the signing key will be in one place. An attacker can go and compromise that single place and steal the key. With MPC, we have a distributed manner, and an attacker needs to compromise many different parties. And that is one of the important pieces of advantages that MPC has. So I'm going to go over this again, but this time slowly and gradually, just to make sure that we all understand what is the role of the MPC and what do we get out of it. So let's assume that you have a normal wallet. You would go and generate a signing key using that wallet. So that, and then you generate an ECDSA signature using that signing key. Okay. As I said, the problem here is that signing key is sitting in the memory of a single machine. And if the attacker can compromise that machine, then we are in bad situation. And compromise can sometimes mean stealing the key. Compromise can sometimes mean just hacking the system and changing the destination and address. So you think that you are signing on a transaction, sending, for example, 1 ETH to the address that you know and trust, but in reality, you are sending hundreds of ETH to another address. So I just want to make sure that by compromise, it could mean many different things. It's not just stealing the signing key. So because we have this single point of failure, now we want to distribute it and make it harder for the attacker. So we are going to split that signing key and give different machines different portions of this signing key, or in more cryptographically speaking, we want to give secret shares of the signing key to different machines. And these machines, if we are careful, these machines will be different environment. For example, machine 1 could be an AWS server. Machine 2 could be a Google Cloud. Machine 3 could be a laptop, for example, a wallet extension. And machine 4 could be a mobile. So different environments, different location in the hands of different people, which makes it very hard for the attacker to compromise them all. It's very hard for the attacker to go and compromise all of them and steal all of them. It is going to be very hard for the attacker to trick all of these 4 different machines into signing something else. Okay, so that's the main selling point. Now, to get to this position, we need to use various MPC protocols. In particular, we need a distributed key generation, or for short, DKG. I'm not going to describe the details of DKG here, but assume that there is a protocol that when you run it, each of these parties will get their proper share in a secure manner. Now, the question is, once you have it, what happens next? You have these shares, you want to generate an ECDSA signature. The naive and insecure approach is for everyone to send their shares into a single machine. That single machine combines all these secret shares together and then generate the signature. It's insecure because we have gone against the rule that all the secrets should not be in one place. Okay, so this is not good. What we do want to have is to have some sort of protocol very similar to, in concept, to that average protocol, the toy example that we have in the beginning, that these machines talk with each other, send messages to each other. Maybe they use some sort of encryption and work with each other to generate the signature. Okay, this protocol, this way of these people communicating with each other is going to be a MPC protocol for signing. In this particular example here, in this demonstration here, this is going to be a threshold signing. Now, by threshold, it means that although we have 4 different parties and 4 different shares, we only need 3 of them to participate. So it's a 3 out of 4 threshold signing protocol. All right. And CBMPC, the open source library that Coinbase has provided, gives you the tools and APIs that you can use to achieve this. So you don't necessarily need to know all the cryptography that's happening under the hood. You just make a couple of API calls on each of these machines. They talk to each other and they run the MPC protocol for you. So, and that's what I will demo shortly in this presentation. But before going to the demo, I want to compare MPC with a couple of different concepts. The first thing is Shamir secret sharing. Shamir secret sharing is a very good protocol or algorithm that is used as part of an MPC protocol. But on its own, it is not an MPC protocol and it's not secure for our needs. Why? Because in Shamir secret sharing, you would go to in a single machine, generates a signing key. Okay, then secret shares it, splits it into many parts, and give each share to different machine, and then at the end put all those shares back together again in a single machine so that it can generate an ECDSA. So By now, you should be familiar that having full secret in one machine is a no-no when it comes to MPC. So Shamir secret sharing on its own is not a fully secure MPC protocol, but it is quite useful as part of a full protocol. The next thing that I want to compare and contrast is MPC with multisig. Okay, and they both have their pros and cons, and they are useful for different situations. And in fact, it's best if you use them together if you want maximum security. So in the MPC world, as we discussed, there are a couple of machines. They talk with each other. They, for example, open a TLS channel, MTLS channel, and they directly talk with each other, send messages to each other. And then at the end, a single signature comes out. And that signature that signed the transaction can be submitted to a blockchain. In this way, we are chain agnostic. We can generate the signature for any chain we want. All that logic is off-chain. And then we end up submitting a single transaction. And we can implement all these concepts of threshold signing, who is going to participate, who is not going to participate. All that logic will live off-chain. In the multisig, that logic should be implemented somewhere. And that somewhere is going to be in a smart contract in blockchain. And those machines are not going to be talking with each other directly anymore. They're going to talk without a smart contract. So they need to submit transactions. Each of them individually need to submit a transaction to that blockchain. So we are fully on chain, and all that logic is going to be tied to a specific blockchain. And if you want to work with multiple blockchains, you need to create multiple smart contracts. And each of your machines need to have the logic to work with multiple blockchains. All right. Of course, this means that when you are in the MPC world, you pay less gas. You just do one transaction. In multisig, you pay more gas because it's multiple transaction, and the logic, that complicated logic of handling these threshold concepts, all lives inside a smart contract. The other difference is the public accountability. So in multisig, you have public accountability. It's clear who did what, when, and if something goes wrong, you know who was responsible. In the MPC world, there is no public accountability. Everything is off-chain. But this is not necessarily a bad thing. So in some situation, you may want to hide the privacy, hide your signers. You don't want anyone to do any on-chain analysis and figure out who your signers are, okay? So to safeguard their privacy, you may choose to do MPC and have your signers live off-chain. Okay, so it's not saying that one is better than the other. In all cases, each of them have their own use cases based on what your requirements are. In MPC, you should be synchronous. So everyone should be online. All those three parties should be online. They should be talking with directly with each other to end up running the protocol. In multisig, you can do it asynchronously. Machine 1 and 2 and 3 could submit their transaction over many days and weeks. And finally, with MPC, you need complex cryptography to properly and securely run this protocol. And in multisig, it's simple. You maybe, for example, any standard signing scheme that would normally work with the blockchain will work here. All right. So with that being said, let's go over a demo. Share my whole screen this time. You can find the steps of this demo in our repository by going to the repository, demos, go, CMD, threshold ECDSA web, and README. This has all the instruction on how you can run it. I'm not going to go over all of that right now. Instead, I just show you the result. So these 4 browser tabs, you can think of them as one machine. So they are essentially different processes running on different ports. And now we want to do a DKG, a distributed key generation protocol, an MPC way of generating protocols. Okay. Now, as I said before, in the MPC, parties need to talk directly with each other. They need a MTLS connection. So in this demo, when you click on connect, these parties are going to talk with each other. establish the connection. Now that we have a connection, we need to configure the protocol. Do we want in the signing phase, do we want 3 parties to participate, 2 parties to participate? How do we want the signing to work? So let's choose 3. They run a protocol among each other. They are the DKG protocol amongst each other. They all get the same public key. So that's essentially going to be a representation of the address, the blockchain address, essentially. And then each of them is going to get its own secret share of the signing key. So those SK1, SK2, SK3, SK4, these are essentially those values. And these are private values to each of those parties and no one else knows about. Now that we have these, we can go to the signing session. In the signing, because we said it is a threshold of 3, we need to choose which 3 parties to participate. And we need to choose what message to sign on. Okay, so let's choose the first 3 parties and then run a signature generation protocol. So this whole thing runs and it outputs a signature. And you can imagine that if you put a blockchain transaction here, then you get a signed transaction as the output, and then you can go and submit this signed transaction to the blockchain. All right. So yeah, this is essentially a demo to show you how this all would look like in practice. And let's see if I go back to slideshow. Can you see it? Okay, great. Okay, so this was a backup. Fortunately, things worked out. I don't need that. Okay, so now here I want to show you how that signing code looks like. The goal here is to show how easy it is to implement and run this protocol without really knowing what is happening under the hood. Okay. So the threshold signing protocol starts by creating a job object. Job is our abstraction over the networking layer. Okay, so essentially define who is who, what's the certificates, and things of that nature. So we have this job object. Now that we have the job object, we do some sanity checks and then hash the message. We hash the message because ECDSA signature requires the input to be hashed. Now, we do this thing, this 2 additive share, and this is because we had 4 parties. Each of them had their own signing keys, but we chose 3 of them to participate. So we need to do some data conversion and convert those shares into proper signing shares. So again, that's another API call that you do and get the proper share. And then just a simple call, just a single call to do an ECDSA sign. And then this runs the whole thing and outputs the signature to you. The rest of that is just conversion, data type conversion to produce a DR signature format. So you don't necessarily need to understand in this quick 30 second of description what is going on. The takeaway that I want you to have is that using CBMPC to implement an MPC protocol, an MPC key management protocol, is very simple. Just a couple of API calls and you're good to go. All right. So by this point, hopefully you have come to appreciate that MPC is a very good fit for key management. And CBMPC gives you all the tools you need to do the typical key management operation. So generate the keys, sign, decrypt, generate verifiable encryption, and many, many more features that I'm not going to go into details at this point. The library is production grade, has production grade security. It's heavily tested, documented, and audited. The core of the library is implemented in C++, but we have comprehensive Go wrappers. In fact, what you just saw in the demo was all written in Go. The library is based on our production code, but it's not an exact replica because, of course, our production code has some part of the code that is suitable for our products. So we had to separate things. It's not an exact replica, but it's very close. The library is highly efficient. If you want, you can go to our benchmark page, and for each of our protocols, you can see the timings that it takes to do various operations. Now, we not only have open sourced the code, we have open sourced all the research that we have done to get to the code. So all the theoretical justification papers that we have done the research on, all the detailed specifications. And if you're interested, you can go to the README file, pick your favorite protocol, and then you can read the theory, read the specification, read the code, and make sure that all of these match with each other. If you're not interested, you can simply just make an API call and have a running application. Now, we decided to open source this library because we believe that MPC is a great fit for key management, as we have talked a lot throughout this presentation. It provides a higher level of security. It removes the single point of failure, makes it very hard to steal the signing key, and also makes it very hard to trick the different signing parties into signing something that they were not meant to do. And now, although we recognize that MPC is great fit for crypto key management, we also recognize that the MPC cryptographic expertise that's needed to implement a proper MPC protocol is very hard to come by. And most of the open source libraries out there don't meet the bar of the production standard. And if any organization or company out there uses something not great and ended up being breached, this breach is going to be bad for the whole field, and by extension is going to be bad for Coinbase. So our hope is that by open sourcing this library, we raise the security posture of the whole field. And of course, we gain trust, more trust from our customers after they see our code, the level of rigor and research that we have put into this. And this transparency is something that we strive for. We also hope to become more secure. When you all look at the code, and if you find any security problem, let us know and submit it through our bug bounty program. And finally, you can find the code under Coinbase/CBMPC and GitHub. It is MIT licensed, so there is no limit on how you want to use it. And with that, I'll end the presentation. Thank you. If you have any question, I'm happy to answer.
Great. Yeah, thanks for the presentation, Arash. We'll move on to some questions now. And for folks that are watching live, feel free to drop a question as a reply to the broadcast, and we'll pick it up and make sure it gets to Arash. But we'll start with a few questions that I had. First one being, can you give us a sense for how much effort went into developing the library?
Yeah, of course. So this was a team of 5 or 6 people working over almost 4 years to lay the foundations, and then making sure that it works internally, and then extracting it out into an open source library. So it was a lot of effort to get to this point.
Cool. And yeah, just one. I think if you stop sharing your screen too, it'll help transition easier towards the end. But all right. So second question is, how should outside contributors responsibly disclose flaws?
Yeah, so there are 2 main ways of disclosing or submitting the flaws, any potential flaws that you find. One is through the HackerOne bug bounty program. So in that sense, you find the program, and all of that is described in the security markdown file in the repository. So through the bug bounty program, you will be eligible for a bug bounty. You submit it. We work together and figure out, validate the problem, and then fix it. But some researchers out there may not necessarily be interested in the bounty. They are more interested in publishing the result. In that case, you can send us an email directly. You wouldn't be eligible for bug bounty. But again, we work together, figure out the timeline, and then you can release the result as your research.
Fantastic. All right, next question. Are there plans to extend the library and add more features?
Yes, absolutely. So we are constantly working on improving this. Sometimes it is implementing new protocol, so a new signing protocol or a new key generation protocol. Sometimes it's just making the existing functionalities easier and more broad. For example, something that we are going to release very soon is that we want to give you the ability so that when you use our Go wrappers, you can connect it to, for example, any cloud KMS provider or YubiKey or whatever you choose. So these are the enhancement and the features that we will release over time as we work on them internally and make sure that they go through audits first and then release them.
Nice. Okay, cool. Last question. When should builders pick two-party versus a T-event threshold? Are there any important differences in the implementation to call out?
Right. So the main thing is whether it's T of N or any, I'm going to use a new term, access structure, or which is going to describe how you want to control your access. So for example, you might say that within your organization, for any high value transaction, you want the CEO to approve and you want the CFO to approve, and either, I don't know, CTO or whatever. I've run out of C-level suits. And other people. So in this structure, you have one party and another party and maybe 2 out of 3 other parties. So you can come up with very complex access structure based on your organization's need, or maybe you are just simply looking for redundancy. Maybe it's 10 of you and you are in different time zones or whatever, and you just at any given time, maybe 3 of you are online or 4 of you are online. Okay. Or maybe it's just you and your customer. It's just 2-party. You're providing a service to you and your customer. It's just the 2 of you. You're always going to be online, and in which case you use it. So it's all depends on the use case and what you want to get out.
Got it. All right, cool. Well, thanks for your time, Arash. Thanks for everybody watching. Please join us next time. We'll discuss how to identify risks through penetration testing.
Thanks for having me.